look at your syllabus, you probably noticed that we have an assignment that is due on the 15th for something called the Wason task. So here's the deal. We aren't going to get to that until after the next exam. So I am going to go ahead and I'm going to move that to after the exam. So it will not be due the 15th. It will be due the 22nd. That's the Monday before Thanksgiving break. If you are not going to be here the Monday before Thanksgiving break, you are more than welcome to not be here. But email me your assignment. I will tell you more about the task as we cover the topic in logic and reasoning. All right. Hi, everyone. I'm so glad you're here. So yeah, that homework assignment has been moved from the 15th to the 22nd. I did put up your study guide for the next exam 2 days early. So it is up, it is ready for you. It will cover semantic memory, everyday memory, problem solving, and then judgment and decision making. And I think for most of you, judgment and decision making, it's one of my favorite lectures to talk about, and I hope it is yours too. We're going to talk a lot about coin flips and gambling and stuff. I don't really gamble. I tried a couple of slot machines at the Las Vegas airport on the way to San Jose. I immediately lost money and I decided to never do it again. Okay. So we are continuing our discussion of problem solving. Right. So the last time we were here, we were talking about the fact that subtle hints can actually help us facilitate insight. So in case you weren't here on Friday, or in case you forgot a little bit about this, this is what is referred to as the pendulum problem. You are brought into a room with two strings that are tied to the ceiling and a couple of other objects, including something like a pair of pliers. Now, the goal while you're in this room is to basically tie those two strings together. The problem with that is that neither of those strings, you're not going to be able to hold one string and also reach over to the side and grab that other string. Like the strings are far enough apart that you're not going to be able to reach both of them at once. And so the solution, the reason that we call it the pendulum problem, is that you're supposed to basically tie the pair of pliers to one end of the string and then swing it like a pendulum until you can actually catch it and wrap it around the other string and tie it. And it's kind of hard for people to figure that out. I was given this problem in my undergrad cognitive psychology class, and I couldn't figure it out. But here's what's really interesting. So sometimes subtle hints can actually help us figure out how to solve the problem. So in one research study, participants were told to basically stretch their arms. And actually, y'all, this really feels good. I got my booster yesterday, so I am super sore, like from shoulders, neck, everywhere. So stretching is really good. For another group of participants, they were told to swing their arms. Now, it's almost like the motion of the arm swinging helped prime these participants to actually end up solving the pendulum problem. And as it turns out, the group that was told to actually swing their arms back and forth actually had a greater likelihood of solving the pendulum problem than people who were just doing stretches. So in addition to subtle hints helping us with insight, prior experiences with problems help us solve this as well. So I want to go back to Dunker's candle mounting problem that we talked about last week. Just in case you may have forgotten, the candle problem is I basically presented you with different objects like matches, a candle, and a box of tacks. And I told you to basically mount the candle to the wall in such a way that wax would not drip on the table below. Now, in the original image, the box is typically full of tacks, and so it can become really easy for us to think that the only thing that this box of tacks is good for is for holding tacks. If you can use a creative solution, you will find that the box can actually be used. You can empty the box and use it to mount the candle. But here's the thing. When you have difficulty solving this problem because you think that a box of tacks is only meant to hold a box of tacks, this is what is referred to as functional fixedness. This is basically, we see the function of an object as basically being fixed. We basically are only going to use an object the way that it was meant to be used. So a box that holds tacks will typically think that the only thing that it can do is hold tacks, when it can actually be used for a variety of different things. Now, for many of us, this functional fixedness comes into play because we're used to having lots of experiences with boxes of tacks. Now, I realize many of you don't really mess around with thumbtacks or push pins all that much, but generally, when I have a box of tacks or a box of push pins, that's where I store them, and that's all that it's for. I've never really thought about using that box for something else. So the more prior experience that we have with an object being used a certain way, the more likely we are to get stuck in this functional fixedness. So the prediction is, if you don't have a lot of prior experience with the object, you will actually experience less functional fixedness. Oops, sorry. And it turns out, if you give this problem to kids, kids actually have an easier time solving this problem than you or I would, because kids don't necessarily, they haven't really gotten locked into using objects only for one thing. To kind of give you an example, when I was a kid, I used to take little paper lunch bags and make like hand puppets, or I would take a big paper grocery bag and cut out the head hole and like armholes, and I would draw a big circle and like a shape inside, and I'm like, ooh, this is my Care Bear costume. So it's like when you're a kid, you're so all of these objects are new enough to you and unfamiliar enough to you that you can think about a lot of different uses for them. But the older that you get and the more that you get used to objects only being for one specific thing, we get more of that functional fixedness. So kids actually have an easier time with the candle mounting problem than you or I would. So we're going to try something. First, I'm going to have some fruit punch, and then I'm going to flip the slide, and then we'll do something. It's warm out there, and we can't shut off the heat now. All right. So I want to talk a little bit about what is referred to as mental set. And to kind of illustrate this, what you're looking at here, you don't need to write this down. This is what is called the water jar problem. So I want you to imagine that you have three different jars. We have jar A, we have jar B, and we have jar C. So here I am being told the capacity of this jar. So for problem number 1, A holds 24, B holds 130, and C holds 3. You must use these jars in order to obtain the amount of liquid specified in the goal column. You may obtain the goal amount by adding or subtracting the quantities listed in A, B, and C. So A holds 24, B holds 130, C holds 3, and the ultimate goal that we need is to get to 100. So what is the way that we could solve problem number 1? Does anybody have an idea? Yeah, Brian.
Could you possibly just subtract 24 from 130?
Okay, so I fill up B, and then I remove 24 using A. So I remove a little bit with A. So that leaves me with 106. So what would I have to do with C? Do it twice, right? Okay, so that's how we get it. Arena, is that what you had too?
Oh no, I was just gonna ask if we had to use all 3 jars.
That's a really good question. Hold on to that. Okay, so number 2, how would we solve that? Here, A holds 9, B B holds 44, C holds 7, and the goal is 21. How would we solve that one? So how many notice that you can do the exact same thing that you did before? You could fill up B, remove A, and then remove 7 twice, right? You could. So we take 44, we subtract 9 from it, and then we subtract 7 twice, and that leaves us with 21. However, did anybody else notice an easier way that we could do this? Yeah.
Fill up C 3 times and put it in B.
Yeah, exactly. So that's a really good question. So when a lot of people do this problem, they get kind of locked into the idea, start with B, subtract A, and C twice. And you can actually do that with problem number 2 as well, but it's really inefficient. It's a lot of work. So you get kind of locked into solving the problem the exact same way, which is why I thought it was really interesting that you asked me, do I have to use A, B, and C? Now, if you get locked into solving the problem this way, it turns out every single one of these problems here can be used solving that method. But sometimes, like you see here, there's a more efficient solution that does not require the use of all 3. So how many of you have had this? Like when you encounter a problem, you tend to solve it the same way that you solved previous problems. Now, does that always work for you? Sometimes no. So when we get stuck in this mindset that the problem has to be solved this exact same way, take B, subtract A, and C twice, we are getting what the Germans refer to as Einstellung, or mental set. It's like functional fixedness, but for problem solving, we get locked into this notion that this is the only way that we can solve the problem. So to kind of give you an example, so some of you who are juniors or thinking about taking research methods know that I've been struggling to make sure that research methods gets offered for my juniors so that they can graduate on time. So I was stuck in terms of thinking it has to be during the spring semester. And then somebody said, what about summer? And it had never occurred to me that that was a potential solution with its own set of problems, of course, but it's one potential solution that I could not think of because I was stuck in it has to be at this time. So sometimes the previous way that we've solved problems is not always the best solution. So what does this mean? It means that our previous experience using a strategy ultimately influences how we solve similar problems, even if it's inappropriate or not as optimal as other strategies. Everybody good? Okay. So let's talk a little bit about how we can get in a better position to solve these problems. And this is what is referred to as representational change theory. So basically, for us to be able to solve these kinds of problems, we need to be able to change how we represent the problems and the strategies to reach the solution for these problems. We need to change the representation that's in our mind to a new one. So this was originally developed by Olson in 1992. And basically, let me talk a little bit about how this works. So the problem representation, the way that you're representing the problem in your mind, is a retrieval cue to help you retrieve potential strategies. So it's basically serving as a means for you to think of potential strategies. The retrieval of these strategies and how to solve the problem involves a spreading activation network. From this, what often blocks us solving the problem is that the current way that we are representing the problem actually prevents us from retrieving the proper strategies and the solution. So by changing our representation, ultimately that breaks our block. And we can do some different things. We can elaborate on the representation. We can relax the constraints of the representation. So let's kind of work through an example that we did in class on Friday, the matchstick problem. So I showed you 6 matchsticks and I said, make 4 equilateral triangles with these 6 matchsticks. You can't break them, and all of the triangles need to have sides that are the same length. So in this case, part of the reason that many of you were blocked in solving this problem was that you were representing the problem as solely having to be flat. You thought that the solution had to be flat and that the triangles had to remain flat. The only way that you are going to solve that problem is by changing how you represent it in your mind. And once I relaxed the constraints and said it doesn't have to be flat, so I actually said, here's another way that you can think about this. You don't have to be so strict in how the solution is represented. Once I relaxed that constraint, for many of you, you were able to solve the problem. So we'll talk about a few different ways that we can actually end up breaking these blocks. So one of the ways, so your book talks about some of the different ways to break the block. That includes things like elaboration, so adding new information, relaxing the constraints, or re-encoding. But another way that we can actually break the block is with something called incubation. So how many of you have found that when you sleep on a problem, you tend to do a little bit better in solving it? How many of you are like me and have found that sometimes your best ideas pop up when you're in the shower? So I actually had a couple of research ideas suddenly just pop into my head while I was taking a shower, and we'll talk about why. So incubation occurs when a problem is solved by ignoring it for some period of time. And you might actually be surprised about that. You might be wondering, well, wait a minute. That means if I have a problem, I can just go for a walk and magically the solution will come to me. Not exactly. You do actually have to do some preparation time. So you do actively have to think about a potential solution for the problem. So I don't know if you know, for example, that people like Albert Einstein actually really enjoyed going on rowboat rides and like rowing in his boat as a way to kind of take a break from work. And actually, he often found that during those times, he would be more likely to find creative solutions. I believe the Kekul, the discoverer of the benzene ring, actually had a dream where he actually saw the chemical structure for the benzene ring. And so the reason that this is suggested to work, Wallace back in 1926 actually said, you've already done all the prep time for this. Your subconscious mind is actually working toward the solution while your conscious mind does something else. So they have actually done research on incubation and whether or not it works. Seo and Ormerod back in 2009 actually did what is called a meta-analysis. Now, for those who do not know, Emily's kind of chuckling because in research methods, we just got finished talking about what meta-analysis is. And don't worry, if you're thinking about taking research methods, you're going to hear about it too, but it won't be very mathy. But the meta-analysis, it's basically a large data study of many, many studies. So you're basically doing a data analysis of data analyses that have already been conducted on a similar topic. So you're looking at the findings from tens, even hundreds of studies. And Seo and Ormerod actually found that there is a small but significant effect. Now, what they ended up finding, incubation effects were reported about 73% of the time, but I did say they were small. Generally, prep time is really critical for you to be able to reach the solution, and for incubation to help with that, you do actually have to spend some time thinking about it, getting background information, trying to work toward the solutions. Additionally, Seo and Ormerod actually found that this works better when you're dealing with a creative problem with many solutions. So this may not work for a math problem where there's only one solution, but if you're trying to design a research study, there are many different ways that you could design a study to come up with the effect that you want. And I've often found that incubation often tends to work best for me when I'm coming up with research study ideas because there's more than one way to do them. So let's talk a little bit why incubation works in the context of representational change theory. So Herb Simon back in 1966 said that part of the reason that incubation works as it does is because you've been sitting here for a while trying to solve this problem, and the strategies that you're using aren't really working. When you incubate, when you take a break from the problem, you actually forget the strategy. You forget the strategy. And so because of that, by forgetting the old strategy that you were using, you can actually adopt a new one. And so it's been suggested that this is ultimately related to interference. In this particular case, this is a study by Penaloza and Cavigo, and they did that remote associates test. So they basically had one group of participants. They either were given clues that emphasized differences between items. And remember, for you to be able to solve this problem, you actively have to look for what they have in common. What's the answer for this one? What's the answer? Our words are tank, hill, and secret. More insight problems. Anybody? It's top. Yep. So tank top, hill top, and top secret. So for you to be able to solve these, you have to think for a word that you have in common. When you're given clues that emphasize the differences between items, that's actively hurting you because you're trying to find a commonality. Or they were given no clues, and they had both of these groups incubate. And what they ended up finding is that incubation only works for the first group, and here's why. This first group that had to emphasize differences, they were given a strategy that didn't work. The second group that got no clues had no such strategy. And so incubation for the first group, they actively had to forget what they had been doing previously to be able to solve the problems. So we find incubation only really helps when misleading information or inefficient strategies can be forgotten. If you aren't trained with any strategies, incubation doesn't really do much. So yeah, you can't just go for a walk and be like, I will magically solve the problem. You do actually have to have some prep time, and you have to have some experience with strategies that have not really been effective. So you can forget about them. So now we're going to talk about the general problem solver. So the general problem solver was developed by Newell and Simon as a computer program that was basically designed to model problem solving in human beings. So it was basically meant to kind of model that. And so oftentimes, remember too, that most of the problems that we encounter in our everyday life are ill-defined problems. We don't always know what the problem is. We don't always know what the solution is, and we don't always know what the strategies are. So kind of keep this in mind. Newell and Simon actually developed a computer program that is solely for well-defined problems. Problems where the start state, the goal state, and the strategies are already specified. So already, this looks like a very, very specific, very small subset of the kind of problems that you and I are capable of doing. Now, much like human beings, they equipped this computer program with serial processing, so only one step could be processed at a time, limited short-term memory, as well as retrieval from long-term memory. So in addition, they specified what is called a problem space, and they modeled this off of what human beings do with something called a think aloud protocol. So here's something really kind of interesting. Do you remember at the very beginning of the semester when I talked about introspection? The idea of reflecting on your own thoughts and your feelings while you're encountering something and why that's bad. Well, it turns out if you train your participants well, you can actually get them to report how they are thinking about solving a problem. And you do this by training them to report all of their thoughts as they work through a problem. So Simon actually developed this methodology, and he calls it a think aloud protocol. So the problem space for most people is represented with a couple of different things, much like what we would see for well-defined problems. The problem space includes the initial stage of the problem, so where we're starting, our goal state, which is where we want to end up, and then our mental operators, which are the different types of strategies that we can use to solve the problem. So this ultimately is kind of comparing problem solvers to people trying to kind of work their way through a maze. So you're basically taking a mental journey. You start at the beginning of the maze, you have an endpoint in the maze, and then you have a variety of different operations that you can do to help you navigate that maze. So we can kind of look at the general problem solver in action. So Newell and Simon believed that we solve problems in one of two different ways. One of the first major ways that we solve a problem is with what is called, you're just really low in that chair. With something that is called a heuristic. You can kind of see me wiggling my thumbs because a heuristic is what is called a rule of thumb here. So for example, so a heuristic is basically just a really quick way to solve a problem. Generally, we're going to use heuristics more often than not because they don't make a lot of demands on our cognitive processes. And generally, they're going to be pretty accurate. So they're very quick ways of solving problems. But because they are not cognitively demanding, sometimes we are going to run into biases or errors. So they don't necessarily have they don't require a lot of effort, but they are prone to errors. On the other hand, we can do what is called an algorithm, and we will talk about these two problem-solving heuristics in a second, means-end analysis and hill climbing. With algorithms, all possible outcomes are computed. So here's what this means. So your book kind of gives the example. If you named a 5-letter bird ending on the letter P, an algorithm would basically generate all 5-letter sequences of birds and then search through them all to get P. So they would list all of the different possibilities of 5-letter words, and then they would pick the one that ends on P. So they would go through all possible combinations. So you will eventually get the answer with an algorithm, but it's going to be really time consuming as a result. So in the Tower of Hanoi problem, I kind of showed you this puzzle recently. So we've got all of these discs sitting on 3 different pegs. And what you're basically trying to do is recreate this tower on the 3rd peg. So the rules are that you can only move one disc at a time, and you can't put a larger disc on top of a smaller disc. So if I was doing an algorithm, I would basically work through all possible moves until I got the correct sequence. Now, for my Tower of Hanoi that I have in my office, I believe it takes about 127 correct moves to get to the solution. So think about an algorithm. An algorithm is going to work through all possible moves, not just the ones that are correct. It's going to make sure we get the right sequence. So that's going to take a lot of effort. On the other hand, I could do a heuristic that basically says, I'm always going to make sure that I'm making progress with every move that I make from peg to peg, and I'm not going to go backwards. So that can work, but it can also lead to errors. So hill climbing is a heuristic where you are always trying to get closer to the goal. Every step gets you closer to the goal. The problem with this, okay, that's getting really loud. When I hear other people talking, it makes it really hard for me to kind of focus on what I'm trying to say. It's a little distracting. So the idea here with hill climbing is that you're always going to want to get closer to the goal. Every step you take is one that gets closer to the goal. So take a look at this cute little dog. I'm pretty sure that's a dachshund. One of the biggest problems with the hill climbing strategy is that it doesn't allow for backwards movement. So you can kind of read the caption here. According to the hill climbing strategy, the dog should, at each step, choose a path that moves it closer and closer to the goal. However, this strategy will fail. So the dog's right here, the bone's right there. For the dog to actually get the bone, he actually temporarily has to move farther away from the bone, moving backwards a little bit before it can get to the fence and get inside. So the dog needs to move away from the bone in order to reach the bone. So hill climbing, we're always trying to get closer to that goal. A means-end analysis is a different heuristic. So in the means end analysis, you are going to notice the differences between the current state and your goal. And from that, you're going to form a sub-goal that reduces those differences. And you're going to keep doing this until you reach the goal. So you're constantly going to be evaluating where you are and where the goal is. You're going to create a sub-goal that meets that first step. And then you're going to make a new sub-goal that's going to ideally get you closer and closer to that goal. So for example, imagine that I need to go on a flight to New York. But to get to New York, I first have to take a connecting flight down to Florida. Now that effectively takes me farther away from the goal of New York City. Hill climbing won't permit that. I can't move backwards with hill climbing, but with a means end analysis, I can say, okay, my first sub goal is to get to Florida. Once I get to Florida, I can then take a flight to New York. So an example in your book, suppose your wash basin is leaking. I assume they mean a sink. So suppose your sink is leaking. Your problem-solving strategy after having held your finger against the leak a few times, most probably will be to find someone who can fix it or someone who may know someone to fix it. So we have these sub-goals. Ultimately, our goal is to fix the sink, but because we ourselves cannot do it, we create a sub-goal that says, call your plumber, and then the plumber can fix it. We do this a lot. So is the general problem solver a good model for what we do? Well, it's good for well-defined problems, but unfortunately for human beings, and as I've already mentioned before, most of our problems are ill-defined. We don't always have the strategies available to us. We don't always have a solution readily apparent to us. So most of our problems are actually ill-defined, and GPS can't really tell us a thing about that. Additionally, it doesn't tell us anything about insight. We don't really know how insight works from the perspective of the general problem solver. Additionally, it does tend to specify the shortest sequence. So GPS is always going to give us the shortest sequence to the goal. And I don't know about you, but when I've been able to solve problems, I don't typically take the shortest sequence. I take the longest one, the one that meanders and kind of wanders around the most before I get the solution. Now, because of the composition of the GPS, remember that it has a good short-term memory and a long-term memory. So it can remember prior steps very well, but it's not good at planning future ones. It has the capacity to remember the past, but it doesn't have the cognitive capability to plan for the future, which is a lot of what you and I do. So it's okay. It doesn't really quite look like how you or I solve problems for sure. Everybody good? Okay. So now let's talk about transfer. So when we learn a solution to a problem, can that carry over to other future problems? So transfer occurs when we use our previous experiences from solving a previous problem to help us solve a similar problem. And this is what is referred to as positive transfer. So positive transfer occurs when we actually use our previous experience to help us solve something similar, and it's effective. But sometimes we do find that previous experience can actually hurt problem solving, and this is what is referred to as negative transfer. So positive transfer facilitates, negative transfer inhibits. Doctor.
What is the title of this?
Oh, let me see. Are you having trouble finding it on e-learning?
Oh, I haven't.
Oh, you do?
I haven't looked at it.
Oh. Oh, okay.
But I just missed the title of
Oh.
what we're talking about right now.
Oh, okay. Okay. Yeah. There you go. Sorry about that.
Oh, that's fine.
Oh, not a problem. Okay. Are we good with this? Okay, so let's talk a little bit about the importance of transfer. So transfer is important. Ideally, the information that you're learning here and in your other classes should help facilitate learning outside of the classroom or beyond the classroom, even in topics that are not similar. So I've been teaching you a bit about how you think, how you learn, how you remember things. You can take this information and use it in a wide variety of situations. And it doesn't necessarily have to be related to cognition. So this is ideally what we want to happen. This is what is called far transfer. So information that we learn carries over to dissimilar topics. That's why we call it far. It's dissimilar. Now, here's the thing. Many studies that we're going to look at focus on what is called near transfer. They have a similar context. So what you learn in this cognition class may help you with other psychology classes, but it may not necessarily help you with history class, is kind of the idea, if we're talking about near transfer. So here's a quick question. How many of you have heard of different brain training programs? Okay. When I was starting my postdoc at Georgia Tech, brain training programs like Lumosity were kind of all the rage. And the idea was that you could do these different cognitive tasks, you could do these little puzzle games, and they would actually cause your brain to basically become better at problems that were completely different. So some people actually report that games like Lumosity raise your IQ like a couple of points. So if we do brain training, we can actually raise your IQ. So we teach you these little games, but it has a net effect on everything you do. So a lot of these people were believing that brain training programs create far transfer. You're doing this little program where you have to keep track of different objects, but it turns out you can use this in your everyday life. So they were saying it was far transfer. Here's the problem with brain training programs. The brain training programs, like things like, and let's be clear, I have Big Brain Academy on my Wii. It's a lot of fun, but it's just games. But here's the thing. Brain training programs that give you those kind of puzzles and those games, they don't improve your IQ. They only get you better at doing those games. So we have near transfer, but we don't really have far transfer. So with brain training programs, I would look it up. It was the biggest scam and it made me so mad. It made me so mad. It'll just get you better at the tasks that you're doing. It will not carry over into other unrelated things. We've got near transfer, but we don't have far transfer. So there are 3 different dimensions that we have to think about when we're talking about transfer. So first of all, we have how similar, if we want transfer, how similar are these tasks to each other? And that doesn't just include the structure of both of the tasks. It also includes their superficial features. There's also context. Is there similarity in the location or in the social context that we're in? And additionally, we have time interval. What is the period of time between the past problem and the current problem that you're trying to solve? And we generally find when we look at these 3 different dimensions, transfer tends to be best when the problems, so the task and the context are similar and the time interval is really short. That's when you're going to get the best transfer. So we're largely going to talk about transfer in the context of analogical problem solving. So for example, your book kind of talks about the fact that when y'all probably first learned about atoms, you probably learned that electrons revolve around the nucleus of an atom, like the planets kind of orbit around the sun. Now, do electrons actually do that? No, we know that now, but it's a very helpful tool to kind of help us think about these objects. So we're going to talk about transfer with respect to analogy. So we only have 1 slide left. I don't want you to write this down. I kind of have it's not homework. You're not required to do this, but I'm going to read through this problem and I want you to see if you can come up with a solution by next class, because we're going to open with this problem. Okay. In a village by a river, a chief guards a sacred stone statue. Every year, the chief goes downriver to the village to collect taxes. There, he places the statue in a tub at one end of a hanging balance. To pay taxes, villagers fill the tub on the other end of the scale with gold until the statue is balanced. This year, the chief forgot to bring his balance scale. How can he figure out how much gold to collect to match the statue's weight? So I'm going to stop here, think about a potential solution to this problem, and we will open with this next time. Bye, everybody.